We now have a lot of experience finding the areas under curves when we're dealing with things in rectangular coordinates. And we took the Riemann sums, a bunch of rectangles, we took the limit as we had an infinite number of infinitely thin rectangles, and we were able to find the area. But now let's move on to polar coordinates. And in polar coordinates, I won't say we're finding the area under a curve, but really in this example right over here, we have a part of the graph of r is equal to f of theta, and we've graphed it between theta is equal to alpha and theta is equal to beta. What I want to do in this video is come up with a general expression for this area in blue. This area that is bounded, I guess you could say, by those angles and the graph of r is equal to f of theta. And I want you to come up, or at least attempt to come up with an expression on your own, but I'll give you a little bit of a hint here. When we did in rectangular coordinates, we divided things into rectangles. Over here, rectangles don't seem as obvious because they're all kind of coming to this point. But what if we could divide things into, sector, I guess we could say, little pie pieces. Someone's doing some serious drilling downstairs. I don't know if it's picking up on the microphone, but anyway, I will continue. So what would happen if we could divide this into a whole series of kind of pie pieces? If we could divide it into a whole series of pie pieces, and then take the limit as if we had an infinite number of pie pieces. So we want to find the area of each of these pie pieces, and then take the limit as the pie pieces, I guess you could say, become infinitely thin, and we have an infinite number of them. And I'll give you one more hint. For thinking about the area of these pie, I guess you could say pie, the area of these pie wedges. I'll give you another hint. So if I have a circle, I'll do my best attempt at a circle. Luckily, the plumbing or whatever is going on downstairs has stopped for now, allowing me to focus more on the calculus, which is obviously more important. All right. So if I have a circle, that's my best attempt at a circle, and it's of radius r. And then let me draw a sector of this circle. It's a sector of a circle, so that's obviously r as well. And if this angle right here is theta, what is going to be the area? What is going to be the area of this sector right over here? So that's my hint for you. Think about what this area is going to be, and we're assuming theta is in radians. Think about what this area is going to be, and then see if you can extend that to what we're trying to do here to figure out somehow, I'm giving you a hint again, using integration, finding an expression for this area. So I'm assuming you've had a go at it. So first let's think about this. So what's the area of the entire circle? Well, we already know that. That's going to be pi r squared, formula for the area of a circle. And then what's going to be the area of this? Well, it's going to be a fraction of the circle. If this is theta, if we went 2 pi radians, that would be the whole circle. So this is going to be theta over 2 pi of the circle. So times theta over 2 pi times theta over 2 pi would be the area of this sector right over here. Area of the whole circle times the proportion of the circle that we have defined, or that the sector is made up of. And so this would give us, the pi's cancel out, it would give us 1/2 r squared times theta. Now, what happens if instead of theta, so let's look at each of these over here. So each of these things that I've drawn. So let's focus just on one of these wedges. I will highlight it in orange. So instead of the angle being theta, let's just assume it's a really small angle. We'll use a differential, although this is a little bit of loosey-goosey mathematics, but the important here is to give you the conceptual understanding. I could call it a delta theta, and then to eventually take the limit as our delta thetas approach 0. But I'm just going to, just for conceptual purposes, assume we have a infinitely small or super small change in theta. So let's call that d theta, and the radius here, or I guess we could say this length right over here, you could view it as the radius of at least the arc right at that point. It's going to be r is going to be r is a function of the thetas that we're around right over here. But we're just going to call that our r right over there. And so what is going to be the area of this little sector? Well, the area of this little sector is going to, instead of my angle being theta, I'm calling my angle d theta, this little differential. So instead of 1/2 r squared, it's going to be, let me do that in a color you can see, this area is going to be 1/2 r squared d theta. Notice here the angle was theta, here the angle is just d theta, super, super small angle. Now, if I wanted to take the sum of all of these from theta is equal to alpha to theta is equal to beta, and there really is an infinite number of these, this is an infinitely small angle, well then for the entire area right over here, I could just integrate. I could just integrate all of these. So that's going to be the integral from alpha to beta of 1/2 r squared, 1/2 r squared d theta, where r, of course, is a function of theta. So you could even write it this way. You could write it as the integral from alpha to beta of 1/2 r of theta squared d theta. Just to remind ourselves, we're assuming r is a function of theta in this case.